Monday on a 5-day week. I don't wanna work this sheet. Yeah, yeah. Okay, so we're doing problem 2471. Minimum number of operations to sort a binary tree by level. All right. You are given the root of a binary tree with unique values. In one operation, you can choose any two nodes at the same level and swap their values. Okay, well, this is already indicating that we should do breadth first search. So I already know from just looking at this problem that we're going to be doing breadth first search because I keep seeing the word level and choose any two nodes at the same level, right? And breadth first search is a natural algorithm to find nodes at the same level, right? So return the minimum number operation needed to make the values at each level sorted in strictly increasing order. Okay. The level of a node is the number of edges along the path between it and the root node. Okay. So let's look at this example. We have 1, 4, 3, 7, 6, 8, 9, 5, 10. So let's first ensure that we understand what this word level means in this context, right? So you call this level equals 0 here. And that just means all the nodes that are 0 distance away from the root. Level 1 then is then all the nodes that are a distance of 1 away from the root. Right? All these nodes are distance 1 away from the root. And so on and so forth. Level 2 is all the nodes that are, well, we got distance of 1, distance of 2, distance of 1, distance of 2, distance of 1, distance of 2, 2, right? Distance 2 away from the root. And then finally, level 3, right? Because all these nodes are distance of 3 away from the root. Right, and this problem would also note that it's all about the distance from the root, right? So, if you had an additional node here, right, this node would also be level 3, right? Because it's a distance 3 away from the root. So there's really two parts of this problem, right? We need to get first thing we need to do is get the nodes at each level. And the second thing we need to do is find the number of swaps, right? Because this is saying the minimum number of operations need to make the value in each level sorted. In one operation, you can choose any two nodes at the same level and swap their values. So that basically means how many swaps does it take required to find the number of swaps required to what? To sort the level. So let's first address this first point. First. Let's address this first point. So how, when you look at array at a tree, can you find nodes at each level, right? Well, I think a natural candidate for this problem would be, like I said prior, breadth first search, right? Because breadth first search will traverse all the nodes at a level prior to traversing nodes at the next level, right? So breadth first search will look at all these nodes before it looks at these nodes. And it'll look at all these level 1 nodes before it looks at these level 2 nodes. It'll look at all of these level 2 nodes before it looks at this level 3 node system. Right? And how does it do that? Well, what it does is it has a queue, right? And the queue will add this, and then process this. And since it's processed this, it'll add these. It'll process this and add these. Then it will process this, no neighbors, process this, no neighbors, process this, no neighbors. Process this, does have a neighbor. Process this, does have a neighbor. Process no neighbors, process no neighbors. So if you notice in that little short example I did, I never had a situation where there was something on the, I never had a neighbor that was greater than one away, and I always had systems that were processed that were of the same level, right? Like I never had a situation where the queue had something that was greater than one level away, because something that's greater than one level away will be processed after everything at the same level has been processed. So that's how BFS works. So let's use BFS to get a level order traversal, and I'll just show you a standard code that I've seen a million times, and you should probably just memorize. So if you wanted to use BFS to get the level order traversal of everything, well, you can then just say, well, you create a queue with the root inside, and while there's a queue, right? So this would be the level 0 here is inside of the queue. We're going to do something. This is where part 2 is, right? Because the queue is going to be everything at the same level. So we're going to find swaps, but we're going to do that next. Let's just first do this level order traversal. And you say queue equals what? So say the queue was at level 1, right? So if we were at level 1, the queue would equal 4 and 3. So what we should do is look at each node if we want to get to the next level and have the queue be the children of these nodes, right? So we're going to look at each node and add its children, right? Because after this operation's done, the new queue will be 7, 6, 8, 5. Right? Because it's going to add 4's children and it's going to add 3's children. So what we do is we look at each node. So we're going to add each child. We're going to look at each node in the queue. And then we're going to look at each child for each node in the queue. And what are the children? Where there's the node's left child, since this is a binary tree, and the node's right child. And we're only going to add it if the child exists, right? So for example, if we were looking at this node here, and we wanted to add both of its children where it doesn't have a right child, right? So we'd only add this left child. So we check both possible children and we only add them if they exist. Right? So we say, okay, if you have a left child, add that one. If you have a right child, add that one. So if we're looking at the queue and we add the children of all the nodes in the queue, then the queue will be equal to this in the next operation. And you can see that. So what we'll do is, just for the sake of, we're going to remove this level, but I'm going to use this for debugging so you can see how this works. Level equals 0. We're going to print level. We'll say level plus equal 1. And then we'll print node.val for node in queue, right? Because then the queue is going to have tree nodes in it, so you don't want to print the whole thing. Okay, so you're going to see here, right? So for this tree here, right, at level 0, we have node 1. At level 1, we have 4 and 3. At level 2, we have 7, 6, 8, and 5. And at level 3, we have 9 and 10. So this works beautifully. But that's the first half of the operation, right? So now we've successfully found a way to look at each level. And we need to look at each level because we want to make the values at each level sorted in strictly increasing order. So we need to kind of compartmentalize, right? And look at each level individually and find the operations that need to happen. Then look at the next level and find the operations that need to happen, and so on and so forth, right? So this is really just a system of independent problems. And now we've determined each of the independent problems because we found each independent level, right? And we're switching the values, not the actual tree node. So like, it's not like swapping this will change the array, right? If I swap 4 and 3, see if I can get this back to something that's at least halfway decent, not looking so crazy. And if I will always love coding. Okay, that looks fine. So, the idea is that we're swapping these values, not the actual nodes, right? So if I swapped, because I'm going to have to swap 4 and 3, right? Because they're out of order. The tree looks like this, right? I'm just swapping the values of the node, not the whole entire tree, right? Because there's more difficult problems, probably. I'd have to think about how you would do that. But there's more difficult problems where, like, swapping this is actually swapping this entire system. That's not what's happening here. We're just swapping the values of the nodes. But notice how these things here are still the same, right? So we don't have to think about, like, what happens next. We're just swapping the individual values. So we look at these values, make a decision. Look at these values, find out how many swaps we have to do, so on and so forth. So what we'll do is we'll look at the queue's values, and we'll make it a way of, well, let's have a count be the number of swaps. And then we'll say count plus equal what? Plus equal the swaps in this array here. For this array, and then we'll create a new function called swaps that takes in a list, and it finds the number of swaps necessary to make a list sorted. Okay, so we'll get the number of swaps here. We don't need this anymore. We'll take the new queue, and then at the end, we'll return count, because count will have the number of swaps we had to do total, right? Because at each level, it'll add the number of swaps at that level, and then we look at each, and then we sum up the levels in the count, and at the end count will have that value. So how do we find the number of swaps in a list efficiently? So there's an n log n solution, which makes sense because it's kind of like a sorting problem. Let's look at, so at some point in this operation, we're going to be looking at 7, 6, 8, and 5, right? So when I look at 7, 6, 8, okay, now it's a list, so let's just make it like this. So if you had a list, right, 7, 6, 8, 5, how many swaps would it take to make this list sorted? Well, the thing is like, where do things need to go relatively to each other, right? Like this, you have these positions, right? 0, 1, 2, and 3. And then you have these values, right? And 5 is supposed to be in the 0 spot, 6 is supposed to be in the 1 spot, 7 is supposed to be in the 2nd spot, and 8 is supposed to be in the 3rd spot, right? Those are the spots that they're supposed to be in, right? 7 needs to be where 8 is, 8 needs to be where 5 is, 5 needs to be where 7 originally is, right? So one way you can look at this problem is say, well, for sure, right, like greedily, 7 needs to be where 8 is. So I'm going to have to move 7 over there eventually, right? So I'm going to have to take 7 and put it over where 8 is, right? But then when I look at 8, well, now 8 needs to be in the 3rd slot. So if I move 7 to 8, I'm going to have to move 8 somewhere else, right? Because if 7's not in the right spot, it needs to be in 8's spot. Well, that means that 8's not in the right spot as well, right? Like you're getting pushed over, right? Like, because if I'm not in the right spot, that means I need to swap with somebody else. So whoever's in the place that I'm supposed to be, they're also not in the right spot. So then 8 needs to go somewhere, and 8 needs to go where 5 is, right? Now, if 8 has to kick 5 out, then that means 5's not in the right spot, and 5 needs to go where 7 is. Well, now we have a cycle, right? Because like A needs to be in B, and B needs to be in C, and C needs to be in A. Well, then that means that everybody kind of figured out where they need to be. Okay? So if you have a cycle and 6 is in its own spot, so it's good. Well, to make this work in terms of swapping, I could just swap values backwards, right? I could look at this length here and swap them. And then I can just look at, I'll draw it. I'm trying to figure out exactly the best way to do this. And I have this link here, kind of. And then I just draw this one, and I swap those. And voila, it's magic. Now you have a sorted array. So the idea is if you find a cycle, right, by doing this kind of greedy process, you just find the length of the cycle minus 1, and that'll be the number of swaps, because you can just back propagate these edges, right? Like, okay, you swap these ones out here, then you swap these ones out here. So it just really just kind of boils down to that being the process for finding the number of swaps. It's really just the length of all the cycles. So the first thing you need to do is you need to take the list and find out where everything needs to be relative to the system, right? Like the first thing I did is I found out, right, where these things need to be relative to each other, right? Like 7 needs to be in the second spot, 5 needs to be in the 0 slot. So that's equivalent to just taking the range. So position equals sorted range length of list, and then the key is lambda, I guess it's an index, and then the list at the index value. So that's the position of everything. And then it just becomes like kind of like DFS a little bit. I'm trying to think of the best way to do this. So, so cycle lengths. Sorry, I'm just trying to think about how we're going to do this. Cycle lengths equals 0. And then we can look at each node in the range for index. We need a visited array, actually. Right, because we need to find out if we created a cycle here. Right, here I know I've created a cycle because I've gone back to a value I've already traversed. So every time I traverse a value, I can set its visited value to 0. So you'd say visited at IDX. Well, if it's already been visited, then it's part of a cycle. So visit IDX, continue. Visited IDX equals 1. Or no, you'd say while JDX, I guess. I don't know, man. Damn. JDX equals IDX, and you could say while visited JDX equals 0. Let's say cycle lengths plus equal 1. Visited at JDX equals 1. And then, I'm doing this really stupid. And then JDX. So where does it need to go? Well, that's the position of JDX, right? Because that's the place where it needs to go in the system. And then you overcount the cycle lengths by 1. And then you return cycle lengths. Now this can definitely be shortened significantly, but let's just say that for the sake of the problem so far, we'll start there and see if that works. All right, let's submit that. We will talk about it. All right, cool. So how do we make this a little bit better? Because it's kind of crazy. So we could say if not visited IDX. We don't need to do that. We can just change the value of IDX here because it'll get updated after, so we don't need to do like, and we'll say cycle lengths equals cycle lengths plus 1. So every time you traverse a neighboring node, you add 1 to the cycle. Visited of JDX equals 1. Now it's IDX. And then we look at IDX's neighbor, which is position of IDX. And that means you can just put this all in line and pray, because I just did a lot in a short period of time. Kind of wondering if this needs to be the last. This won't change anything. Not enough values to unpack. -2. RDX equals problem is if you try to do one-line solutions, then you have like something and then something else, you know. We'll just put it back. We'll make it a little bit shorter, but not that much shorter. Damn, dude, what did I do wrong? I bricked my own code. I had it working, and then I decided, no, you know what? I'm gonna brick it. Oh shoot. Alright, well, for whatever reason I can't get that shorter, so we'll just go here and do this. We can make this shorter. I'm telling you. Sorry, guys. I'm sorry that I decided that I wanted this to be the world's shortest solution when it just wasn't necessary. It's funny how the runtime, don't even worry about it. It's just crazy. It's like not even accurate. Like not even right. Well, it's just such a huge variance, so who cares? Just wondering if I can get something to be shorter here. It just seems very, very. Alright, let's put that on one line. You are not signed in. I don't know why it keeps doing that. It's like it disconnects me from the internet, but that's fine. That's gang. So let's just let's take a look a little bit at the runtime, because I probably should have done that before. Well, I need n log n to sort this array, right? And n is the maximum size of the level. And I have to look at each level inside of here. So if n equals the max length of a level for level in tree, we'll just say that. I have to do n log n operations, right? And then I have n space because I have to have n in the queue, and then I have to create this visit array for n. There you go. All right. Peace out, guys. I'm sorry that this got so janky near the end, but I hope that this was helpful.